just mentioned about the balancing. Let's look at the next single replacement. An iron nail. So a nail is made up of iron, the element. So iron, the element, is just solid iron. Is dropped into a solution of hydrochloric acid. Hydrochloric acid is HCl. And so when I look at this reaction looks like an A plus Bx pattern. It's an A plus Bx pattern. What are the products? The products are going to be AX plus B. Now, we have a choice for iron. So iron's going to go from the element to the ion, the cation in this case. And so our choice is it could form iron 2 chloride or it could form iron 3 chloride. Which one should we go to? Should we go to iron 2 or iron 3? And so if we go back to this chart here, and we look at iron metal goes to iron 2. Do we see an iron metal going to iron 3? No. I see an iron 2 going to iron 3, but that's a subsequent step. And so at least in the first step, iron goes from iron to iron 2. And so what we're going to do is, based on that observation, I would think iron 2 chloride forms, which is going to give us the formula FeCl2. And then B is hydrogen, the element. Hydrogen, the element, is diatomic, so it's going to form H2. All right, H2 is a gas. So is this a driving force? Gas formation driving force? No. For metathesis, yes. For acid base, yes, but not for redox. Because redox involves, again, the Dr. Jekyll and Mr. Hyde, whereas metathesis, acid base don't. We don't have this Dr. Jekyll, Mr. Hyde transformation, which is highly energetic. Chlorides are soluble, except for silver, lead, and mercury, so that's going to be aqueous. Instead, what we have to do for driving force is we compare activities. I'm not going to balance this yet, because first I'm going to look at if there's driving force. If there's no driving force, why bother balancing it? And so we're going to compare the activity of A with the activity of B. Which one's more active, A or B? Iron or hydrogen? Okay, you should be able to look at the activity based on this chart, lithium being the most active. Here's iron, here's hydrogen. Which one's more active? Iron or iron's more active? Or you should be able to base it on this chart. Look, lithium's the most active. See, iron's here in the middle, hydrogen's down here. So iron is more active. And so what we're doing is we're going from more active to less active. Is that favorable? Yes. In other words, less active means more stable. So this is what we call driving force here. And so when we're looking at driving force for single replacement, we're looking at more active to less active. More active what? Well, in this case, it's the more active reducing agent, or less active reducing agent. So we're just looking at the lithium side. Okay, so that's all we need. We have a driving force there. Okay, now let's go ahead and balance it. So how can I balance this equation? I have one iron, I have one hydrogen, but I have two hydrogen atoms here, so I'll need to multiply this by 2. I can't write a little 2 subscript here because that would change the chemical identity. Formula ratio. Formula ratio is going to tell you the composition of the compound. So we got 2 hydrogens here, 2 chlorines. Now everything's balanced. This is the complete equation. Let's write the ionic equation. The ionic equation, we ionize the strong electrolyte. So iron, is it a strong acid? No. Strong base? No. Soluble salt? No. So we leave it alone. So this is going to be iron solid. HCl, strong acid? Yes. So we ionize it. This is going to ionize into 2 H pluses and 2 chlorides, 2 Cl minuses. FeCl2, strong acid? No. Strong base? No. Soluble salt? Yes. So this ionizes into aryan 2 plus 2 Cl minuses. Then we go to hydrogen. Strong acid? No. Strong base? No. Soluble salt? No. So just leave it alone. Hydrogen gas here. Do you see a spectator? Yeah, X is a spectator, the chloride. And so the net ionic equation, we're going to get rid of the spectator. And so it's going to get iron, solid, plus 2H plus, yields iron 2 plus H2 gas. So in other words, the chloride, once we get rid of the spectator, then A is our reducing agent. B is our oxidizing agent, which is H plus. So H plus takes electrons from iron, forming iron 2 plus and hydrogen. We have our reaction there.
So F is the reducing agent and H is the oxidizing agent?
Yes. That's correct. You don't have to identify the single replacement. So this is what we have for the single replacement, and then it's done. We check it to see if it's balanced. We have one iron, 2 hydrogens, 2 hydrogens. So atoms are balanced. Then we check the charge. This is neutral. This is 2 times plus 1 is plus 2. This is plus 2 already. This is neutral. So plus 2 on the left, plus 2 on the right. It's balanced. This is net ionic is balanced. Let's look at the reaction between zinc and copper 2 nitrate. This is a strip of zinc metal being dipped into a copper 2 nitrate solution, which is blue. You can see it precipitate here. Is that precipitation the driving force? Well, let's take a look. So a piece of zinc, so that's zinc metal, so is dipped into a solution of copper 2 nitrate. Copper 2 nitrate, what's the formula for that? Cu NO3 2. It's copper 2 nitrate. Okay. Write the conventional total ionic and net ionic equations for the reaction. So again, this looks like a single replacement. A plus Bx. A plus Bx yields Ax plus B. And so what do we form? We form zinc nitrate. Zinc nitrate, what's the charge on zinc? Plus 2. So same as copper. So it's going to be ZnNO3 2 and B, which is this copper alone. Copper alone is copper metal. No charge, it's not copper metal. Okay, nitrate salts are all soluble. We'll enough for this. Now, we got to precipitate. That black precipitate there was copper metal. That's what we saw depositing in the zinc. It's hard to tell because the color is deceptive because the crystals are so small. But it's copper metal. So is that the driving force? Precipitation of copper metal? No. The driving force is we got to compare A versus B. A is zinc, B is copper. So we consult the activity series. I don't know why I could put the activity series so far back. So let's compare zinc with copper. Compare zinc is here, copper is here. So which one's more active? Zinc, as opposed to lithium. So we're going from more active to less active. Well, less active is more stable, so it's favorable. So we call this driving force here. So this reaction should occur. The driving force is more active to less active. And so let's go on. This is the conventional equation. Let's go on to the ionic equation. The ionic equation, the ionized is a strong electrolyte. So zinc, strong acid? No. Strong base? No. Soluble salt? No. It's just the element. Copper 2 nitrate, strong acid? No. Strong base? No. Soluble salt? Yes, all nitrate salts are soluble, so it's going to split up into ions. We'll get the copper 2 ion and 2 of the nitrate ions. Is it? I forgot to check. Is it balanced? Yeah, it's already balanced. And then zinc nitrate. Strong acid, no. Strong base, no. Soluble salt, yes. We'll get zinc ions and 2 nitrates. And then copper metal. Strong acid, no. Strong base, no. Soluble salt, no. So leave it alone. If I look, what's the spectator? X is the spectator, in this case again. So the net ionic is just going to show the reaction between zinc salt, which is A, plus the copper ion, B, form the zinc ion, plus copper metal. These are aqueous species here. And so, in other words, the reducing agent here is zinc, oxidizing agent is copper 2. So what we're doing here is we're going from this reducing agent to this oxidizing agent, and if we go backwards here, then zinc takes the electrons as the oxidizer, and copper loses it as the producer. And so we're comparing the 2 reducing agents when we look at activities again, with zinc being a better reducing agent than copper. So that's what drives this reaction. Okay, we check if it's balanced. Okay, when we look at the activity series, we see some additional information there. This additional information is just to give you an idea of how reactive these species are. So, for example, lithium, potassium, barium, strontium, calcium, sodium will replace hydrogen from liquid water, steam, or acid. In other words, these metals here are so reactive, so active, that they can react with liquid water. Magnesium, aluminum, manganese, zinc, chromium will not react with liquid water. However, it will react with steam or acid. All these will react with acid. Iron, nickel, tin, lead will react with acid. Copper, silver, palladium, platinum, gold, these will not react with acid. And so where does that come from? Well, that gives you an idea of the reactivity of these metals here. And that's going to come from this chart here. So if I want to oxidize zinc metal, and that's what's happening here. Zinc metal is being oxidized because zinc is losing electrons to go to Zn2+. And so zinc is being oxidized by some oxidizer. And so I want to oxidize zinc metal to take its electrons. Will zinc ion be powerful enough to oxidize zinc metal? No. So we need an oxidizer that's more powerful than zinc ions. Are aluminum ions more powerful? No. How about iron 2? Yes. And so what we can say is that zinc metal can be oxidized by everything above this. And that is iron 2, tin 2, lead 2, H+, tin 4, sulfate, copper 2. Here's copper 2. And so this is what we did. We used copper 2 ions to oxidize our zinc metal to form zinc ions and copper metal. And so we're going to use copper 2 to take the electrons. We're taking the electrons from zinc. Zinc is going to lose those electrons to form copper metal and zinc ions. So, but we could have used other species too. We didn't have to use copper 2. There's a whole bunch of oxidizers that we could have used. Well, just for a frame of reference, we're going to look at water. Is water the worst oxidizer on the chart? The best oxidizer is fluorine at the top. The worst oxidizer must be at the bottom, and bottom of this chart is water. Is water the worst oxidizer on the chart? No, water is not the worst. Actually, water doesn't belong on the bottom. Where does water belong? Does anybody recall? Water belongs. Do you see these three dashes here? That's where you're supposed to place water. I mentioned this before a long time ago, but water is a stronger oxidizer than aluminum 3+ and a weaker oxidizer than zinc 2+. They're actually two separate charts here. And so how I placed that was by this number. This number is minus 0.828. So minus 0.828 places it between this minus 0.763, so that's zinc, and minus 1.676, which is aluminum. And so water belongs here. So water is not the worst oxidizer on the chart. The worst oxidizer on the chart is lithium ion. And so what that means is water can actually oxidize something. If it was worse, then you wouldn't expect it to oxidize anything, like lithium. Well, can lithium oxidize? Anything stronger than lithium metal. Is there anything stronger than lithium metal on the chart? No. Not on this chart. On the other charts, yes. And so water belongs here. That means water can oxidize all these. So for example, if I tried to oxidize magnesium with magnesium, does that work? No. So I need something stronger than magnesium ion. Well, aluminum 3+ works. What comes after aluminum 3+? Water works. Now, so water can oxidize all these: aluminum, magnesium, sodium, calcium, potassium, lithium. And so water can react with all those. In fact, water reacts very violently with sodium. We saw that in Lake Lemoore. And so that's what we have here. Water will react with all these: lithium, potassium, barium, strontium, calcium, sodium. There's a problem with aluminum. Aluminum is on our chart. Water should have reacted with it, but aluminum forms a tough, impermeable oxide coating. And that oxide coating protects it. So aluminum is a lot less reactive when it has the oxide coating versus no oxide coating. Right, now heat and concentration will change things. So for example, steam. If we have steam, steam is even more reactive, although steam's not on that list. And so we have something called standard conditions and non-standard conditions. And so that chart that we have in this chart is based on standard conditions. Standard conditions would be like room temperature, 298 Kelvin, and normal concentration. If we alter that, we can make things more reactive. Like, for example, instead of using liquid water, we use steam. It makes water more reactive, and therefore it can do more. Or if we make things more concentrated, if it's more concentrated, it could do more. And so that alters things. But we don't have to worry about this. We're not going to memorize this. We're just going to look it up in the table. From the table, another reference point is acid here. You can see acid, acid, acid. We'll ignore the steam for now. If we look at the acid, this is what we have. Acid is H+, so this is acid. Now if we look at acid, acid is capable of oxidizing many more metals than water. Water is only capable of oxidizing these very reactive metals. But if we have acid here, we can oxidize lead, tin, iron, zinc, all of them. And so acid is a more powerful oxidizer. It will be able to oxidize all these. However, acid's not powerful enough to oxidize copper. If we look here, here's acid. For copper, we need an oxidizer that's stronger than copper 2. Is acid stronger than copper 2? No. So in order to oxidize copper metal, we need something up here to oxidize it. So let's take a look. So acid will oxidize lead, but it won't oxidize copper. Copper, we need something else. And so this will not react with liquid water, steam, or acid. But we can figure out what things do react with that. So what types of things do react with that? So let's take a look at that. What types of things do react with that are special acids. So what are these special acids? Okay, so normally when we think about an acid, we think about H+, that's an acid, but we also have other acids here too. So for example, if I look at the ion combination sulfate and H+, sulfate and H+ make sulfuric acid. Or if I look at another ion combination, right at the top there. If I look at this ion combination, nitrate and H+ make nitric acid. And so over here I have this ion combination. Hydrogen or chloride and H+, hydrogen ions and chloride, that makes hydrochloric acid. And so when I look over here, do I see hydrogen ions with chloride or chloride ions with hydrogen? I see sulfuric acid here. I see nitric acid because it's ion combination there. I see another acid, which is right here, IO3 minus with H+, which is iodic acid. But I don't see hydrochloric acid. And the reason is because these acids are special. So we'll talk about these acids next time. Are we out of time here? Yeah. And so we're going to talk about those acids, and those acids are called oxidizing acids.